Okay, we are now on the math skills and Excel check-in, and let's go ahead and get right into it. That's bigger than I thought it would be. That's what she said. I know somebody out there watched this video and thought about it. Okay. One, when analyzing a sample of polluted water, a chemist measures out a 25 milliliter water sample with a pipette. At another point in the analysis, the chemist uses a graduated cylinder to measure out 25 milliliters of the solution. What is the difference in the levels of uncertainty between the measurements 25.00 milliliters and 25 milliliters? So 25.00 milliliters versus 25 milliliters. 25 only has two sig figs. One, colors. 1, 2. Whereas 25.00 has 4. 1, 2, 3, 4. Trailing zeros after the end of a decimal point do count as significant figures. And thus, the difference in levels of uncertainty, because this has 4 sig figs, and this only has 2, there are 2 levels of uncertainty. The level of uncertainty in measurements can be represented by the number of significant figures reported. Each of the following state the number of significant figures. So A is 250 milliliters. Because we have a trailing zero at the end here with no decimal point, that means that this is ambiguous. B, a reaction time is measured to be 208.4 seconds. That is just 208.4. Because that zero is not trailing and it's not in front of anything, then that is 4 significant figures. A chemist records a mass of 0.3488. Analysis. This zero is in front, so we don't really care about it. Just care about these guys over here. And that will come out to be 4 sig figs again. Then D, an extraction process, yields 0.023 grams of caffeine. So we have the zeros in front. We don't care about them like my parents didn't care about me. And we have 2 sig figs. 3, when working with either very large or very small values, it is easier to report numbers in scientific notation. Convert the following numbers to scientific notation. A is 0.00000. That's one too many zeros. 2, 3, oh, with another 0, 4, 4. And B is 13,987,342,000. So this will become 2.344. We do the wonderful little squiggly line from the decimal point. Get 5 spaces, which means it's going to be 10 to the negative 5th. Same thing with this thing. Know that this is 9. It's 10. Wait, no, that's not how it works. Yeah. Now that this is 9. And that's 10. So we get 1.3987. Yes, we have to write all these out. 2 times 10 10th. And we're not adding or multiplying, subtracting, dividing, so we don't have to worry about sig figs here. For when working with significant figures and decimal places, there are different rules for multiplication, division, and addition, subtraction. Knowing how to combine them in calculations and obtain the correct precision can be a challenge. Perform the following mathematical operations, giving each result with correct significant figures. Okay, forward's going to probably just start going horizontal at this point. A, multiplication, division follow the same rules. You can only have the same amount of significant figures in your answer as the least amount of significant figures from the, well, from either term in the problem. So we have 173.99 divided by 0.0217. So this has 5, and this has 3. So our answer will only need 3 significant figures. Chuck that into a calculator, we get 8.02. And you can say like E4, you could do lowercase e, could do the good old-fashioned 10 to the 4th. B, we have 82.992 times 0.3890. So we have 5 versus 4. Same thing with division. We can only use the one with the least amount. So the answer is going to have 4. Check it into a calculator. We get 32.28. See, we are out of multiplication division land, and we have subtraction problem 4.872 minus 0.00971. We have 3 here, 4 here. But because but addition subtraction rules, we could only have 3 decimal points. Thus, when we subtract this calculator, we will end up with 4.862. Now with D, we have the combination of addition, subtraction, or addition, multiplication. Thankfully, our sig figs are already given to us. We can ignore the tens because of that trailing 0. They become ambiguous and thus are ignored. So we see that we have 1.93. I'll write down that problem. 180 times 10 to the 9th plus 0.93 times 10 to the 3rd. So because of the addition, this has 2 places. We're going to use this guy over here. Our answer will only have 2 places, and we will get 1.81 times 10 to the 9th. Then E, 6.022 times 10 to the 23rd. Somebody's dealing with moles here. Times 5.97, 10 to the negative 5th. Same rules with the 10s, so you can ignore them because they're ambiguous. We've got a 4 versus a 3. We're going to use the 3 since it's, well, that. And just chuck it into the calculator. We get 3.595134 times 10 to the 19th. But we only need 3 sig figs. So this will become 3.60 times 10 to the 19th. F square root of 1, or 817.035 sig figs. Answer is going to have 5 sig figs. $28.58. Four. just go ahead and divide 4 off because it has a lot of tiny problems. We'll annex this space over here so we can stick a couple more. G is 12.0 to the 1/3. Which anything to the 1/3 is also known as the cube root. So we'll look at the cube root of 12. Because that has 3 sig figs. We can only have 3 sig figs again, and we're left with 2.29. H 10 to the negative 10 or 14 over 4.37. So 10 is ambiguous. At this point, we really don't care about sig figs, but we need to figure out what the heck is going on up here. So we have 4 versus 3. It's going to be 10 to the negative 2.32 due to those 3 significant figures. Which comes out to be 0.00479, or you can write it lightning. There was lightning outside my window. We're not rewriting it as lightning, as amusing as that would be. 4.79 times 10 to the negative 3rd. We're looking at 30.45 plus 43.249. Times 261. Okay, we have two sig figs here, which means this term, or we have 4 sig figs in this one, 5, but this only goes 2 decimal places as opposed to 3, so that means we're going to use this one with the 4 sig figs, 2 decimal places. So this term comes out to be 73.6.70 times, and then over here we have, they go to the same amount of decimal. Wait, no, they don't. This one goes to 3, whereas this one goes to 4. This one has 1 sig fig. So 0.0261 minus 0.007. Only goes to 3, which means that we'll end up with 0.0. One, 9, because that goes 3. So we have 2 sig figs versus 4 sig figs. We're going to use this second one. 73.70 times 0.019. 1.4. That will be answer to I, and hopefully we can squeeze J in down here.
I need to do what?
Basically the same thing. 11.39. Time for a different color. It's getting cramped in here. Plus 40.78 times 0.0781 plus 0. You don't think the Dropbox is working? It might be because it's an old Dropbox. Send out a notification. Zero, 6. And watch out for the order of operations. Both of these have 4 significant figures, 40.78 times 0.0781. We get here, we'll put this in like yellow. Actually, that's even harder to see. We'll just put it like green. One, 5 plus so 11.39 only goes to 2 sig fig, or not, it goes to 2 places after the decimal point, which is what we will use. And we get 14.58. This is question 5, which also has a bunch of parts, but hey, we're like 40% of the way through the thing. Perform the following mathematical operations, giving each result with the correct set of figures, include units of the answer. A good drink of water. Okay. 5 A right here. 1.2 33 atmospheres times 6.91 liters all over 206 10 to the negative second liters atmospheres over kelvins per mole. Mole, but Kelvin mole. And then times 376.0 Kelvin. So the first thing we need to do, we need to cancel out the units and figure out what our end unit is. See atmospheres here, cross these out, liters here, cross these out, and then these two will also cross out, so we end up with moles. We have a 4 times 4, 5 on, but we have a 5 times a 3, so we're going to end up with 3 sig figs. Now we just plug everything into a calculator. And because there's 3 sig figs, we end up with 22.9 moles. Next is B. Ooh, specific heat of water. Which is 4.184. So we're getting a bit close there. Stupid coughing. Totally not COVID or anything. Ooh, we have a pink color. Guess we're using pink now. .184 joules per gram degrees C times 50.0 grams. 67.34 degrees C minus 24.56. So first 67.34 minus 24.56, both have 2 decimal point or 2 decimals after point, gives us 42.78. That's 4 sig figs. 50 here has 3 sig figs, and then our specific heat of water, 4.184, it has 4 sig figs, but we're going with 3 sig figs. So we have degrees C, so that's going to cancel out. And we have grams, that's going to cancel out. We're left with joules. So 4.184 times 50, that's 0, times 42.78. Take it to 3 sig figs, we're left with 850 or 8,500. See how to make this 3. Oh, this 8.50 times 10,000 to the third. Then we have 5C, which here's the standard error. Back to black. I guess we're not back to black. 2.35 grams minus 1.978 grams all over 2.385 grams. So this gram can cancel out with these grams. Times 100%. So 2.385 minus 1.98 all over 2.385 again. Multiply this by 100%, we get 17. Or 4 sig figs, 0.06%. And now have D. Zero point 856. Times 469. -7th. One over moles seconds. Okay. So use the 8.56. That is 3 sig figs. This is 3. So we're going to stick with 3 sig figs. Throw it into the calculator. And we're left with 1.10 times 10 to the -6th. This is going to be 6, gold is very malleable. You know what? We'll save this file. Then go to your file. 6, gold is very malleable, which means it can be powdered into very thin sheets. Decorative gold leaf can be as thin as 10 microns. 24-karat gold leaf is composed entirely of gold atoms. Gold has an atomic diameter of 1.4 times 10 to the negative 10th meters. How many atoms thick is the gold leaf? So, let's see. Okay. So 0.10 microns. Stone pink. 1 micron is equal to 10 to the negative 6th. Negative 6th meters. But since we have 0.1 microns thick for this gold leaf, it's going to be 10 to the negative 7th meters. If gold has an atomic diameter of 10 to the negative 10th meters, how many atoms thick is the gold leaf? So all we have to do is just divide this by our 10 to the negative 7th. Actually, wait, no, that's not right. Got it backwards here. Just divide our 10 to the negative 7th by our 1.4 times 10 to the negative 10th. And we get 714.2. But we only need 2 sig figs, so we're left with 710. or the better sig figs. 7.1 times 10 to the second atoms. I had to box this in. It seems like bright yellow for the box. Stands out more on the page, I guess. Pretty sure that answer is right because I remember it from being last year when I took this course before I dropped out. Convert the following amounts into requested units, giving each result with the correct significant figures. Include units in the answer. 112.99 minutes to days. Okay. So 60 is ambiguous, we can ignore that. But 24 has two significant figures. So we do for A, one 12.99 over 60 times 24. And we'll only have two sig figs when this comes out. We're left with 0.078 days. B, 12.0 microliters to centimeters cubed. Well, 1 liter is equal to 1,000 centimeters cubed. $112, we did that. Microliters to centimeters cubed. Okay. We'll do the fashion dimensional analysis. Yeah. So 12.0 microliters over 1 times, so going up, we divide. It is 10 to the -6, 1. Then 1 liter into cubic centimeters is 1,000. Now, from here, we can already see that we have the 10 to the 6th, the 1,000, that's 10 to the 3rd. We can easily switch this out. Bit switches 10 to the 3rd microliters to 1 cubic centimeter. Boom. So now, when we do this, get this, 12.0 over 10 to the 3rd. Zero dot 0.120. Okay. Let's see. 387.2 kilometers. 7.2 1,000. Let's do 10 to the 6th fifth centimeters in 1 kilometer. Then 2.54 centimeters in 1 inch. Oh, we have 3 sig figs, 4 sig figs. We're going to 3. Actually, just multiply this all together. We get 3. And we get 1.52 times 10 to the 7th inches. 46.7 degrees Fahrenheit to Kelvin. So our formula here is going to be temperature minus 32 ninths plus 273.15 to get Kelvin. So the temperature they give us is 46.7. That's 3 sig figs. 32 is 2 sig figs. Then just leave it at 2. I want to say 5/9 is going to stick it at 1. It's because of the way it's written, but then like you could really just mess around with anything and have a ridiculous conundrum with sig figs. So we'll just say it's 2 because of the 32. So put 46.7 minus 32. That's going to give us 14.7 times 5/9. Plus 273.15. We get 2.8 times 10 to the second Kelvin. Yeah. 83.381 grams of carbon dioxide to moles of carbon dioxide. Okay. Let's see how accurate do we want to get. Let's go 4 sig figs because that's as much as I know in the periodic table. First thing we have to do is find the molar mass of carbon dioxide. So carbon is 12.01. Oxygen is 15.99. Let's keep oxygen 16.00. Then add them together. Well, there's 2 oxygens, so this is going to be 32. You get 44.01 for a molar mass. And then we just multiply this by 83.381. We'll end up with 4 sig figs because of what we did over here. I hope I didn't leave my car windows open. This is going to come out to be 1689 moles. 0.064 moles of ammonia to grams of ammonia. So same thing with E. So I don't think they actually changed any of the values in here from last year. So nitrogen has atomic mass 14.01. Hydrogen is 1.008. So this comes out to be 1703 following sig fig rules. Because this will be 2 after the decimal point. We get 1703, multiply this by 0.064. We're going to 2 sig figs because of these two. We get 1.1 grams. Now I'm going to save this. And we go on the fun Excel break. Okay, so we have a set of masses 48.8839. $49.0099, 49.12, 1121, 48.9342, 49.0338, 48.7798. Then here we can put our standard deviation. Let's go ahead and get rid of all this. Equals stdev dot p open parentheses, like we talked about in, what's it, the volumetric glassware lab. We put our starting cell, so 85. and colon. So selects anything between our two or in this range from A5 to A10. Then average equal average, same sort of thing as the standard deviation formula, A5 colon A10. So standard deviation is 0.10801, and our average is 48.959. Because standard deviation is reported with 1 sig fig, it's just going to be 0.1. Then we would have 49.0 as our average. That 90, we follow the empirical rule of standard deviations. 95% of the data will fall within 2 standard deviations of the mean. So we'll have our low end. And our high. So we'll look at 50. No, 49, 48.9, 50.1. Is okay. We're back off of our fun Excel break. Back here to the whiteboard, and we're at 9. Around each of the following measurements, the indicated number of significant figures include units in your answer. So 9A is rounding this 0.809342 centimeters cubed squared to 4 significant digits. So this is going to be 0.8093 centimeters squared. B, looking at 67.15064334. None of these values are like significant to anything. I think they just had like some poor TA sit there and like randomly press the numbers on the keyboard just to get these values. Anyways, this is going to 5 sig figs. So we'll just do right there. We'll round the 6 up so that this becomes 67.151 milligrams. C235 Kelvin. Set this to 2 times 10 to the third Kelvin. Because if we had any trailing zeros and no decimal point, it would be ambiguous. And if we had all the trailing zeros and a decimal point, it would be 4 sig figs. But it asks for 1 sig fig. The 1.89520 atmospheres to 3 sig figs. .90 after rounding up. Atmospheres. Then we're back to our fun Excel break. Your last task involves using Microsoft Excel to represent your data graphically. Plots are often the best way to illustrate data trends, especially when a large number of your measurements are involved. The table below contains data collected in the analysis of protein content in milk. Standard solutions of known protein concentration were prepared and their absorbance is measured. The absorbance of the milk sample is determined. Excel may be used to explore the possibility of trends apparent in the data. Absorbance will actually depend linearly on protein concentration according to Beer's law, a concept that we'll address later in this course. Plotting the data with Excel will reveal that if this is indeed true for the data above. Once the data is plotted, Excel can calculate an equation for the best fit line through the data points, and this approach is frequently used to construct a calibration curve. Once the calibration curve is known, it may be used to find the concentration of a substance in an unknown sample. I remember that lab. Pain in the ass. So we'll just write down the whole table here real quick. Protein content. And so symbol. That's it. Micrograms per liter. Absorbance. Standard 1, standard 2, standard 3, standard 4, standard 5, standard 6. Oh, hold on, standard 5. Milk. Zero point zero 0.000 10.0 0.133 20.0 .219 30 0.296 40 0.381 milk, questionable moo juice, and 0.183. Okay, construct a scatter plot from the standard samples, making certain that all axes are labeled with units and the plot is titled. Okay. So we do this. We go over here to charts. We insert our scatter. Then, let's see. Title this. First, I'm gonna add some stuff like axes titles. This will be protein content. Just copy and paste that in there. Then say absorbance as a function protein content. Then we want to display linear regression. So we do that by adding a fun little trend line. Click this arrow. Go to our more options. Nope, that's not where we want to go. There we go. Okay, so it is where you wanted to go. You just have to go over here to this little bar graph thing. Then go down here. Display the equation R2 value. So display equation R. display our squared value on the chart. What your chart in the box is a PDF file, so I will just grab this. We will save this picture and chart. See where that's saved. Oh, fuck, I forgot to do the whole Excel thing. Okay, time for an Excel speedrun. Yeah, so in order to get the chart like this, first you got to put like the whole table thing down here. Drag this over here. We will go over here, insert this little scatter bit here. See this fun little chart pop up. You can rename this whatever you want, as long as it makes sense as what's happening here. So we'll say like set this to increases in absorbance as a function of protein content. So here we want axis titles and we want a trend line. Over here to the trend line, click on more options, go to this little bar thing, display the equation, the r squared value. Then we want our axis titles. The absorbance. Here we go. So that's how you make a chart. Then, according to your linear regression, what is the slope of our calibration curve? That's this little bit right in front of the x. Put 0.0093. Then, what is for y-intercept? We plug 0 in for x. It's just going to be this little plus thing over here, 0.0208. Use the linear equation from your regression above to calculate the protein concentration in the milk sample. So all we do is just, okay. Y is our absorbance, so we know that y is equal to 0.183. We subtract our y-intercept of 0.0208, and then we divide by 0.0093 to get our absorbance of 17.441. Because we're looking at 3 sig figs, 17.4. And that's all of math skills. Doesn't take that long.